Hello, we're Team The Thinker, and my name is Chris Beck. The other members of this team are Devin Cosgrove, Andrew Duvall, Warren Tan, and Ryan Eder. On the right, you can see our team, The Thinker, and we are a collective of students from Leland High School known for our thinking abilities and our passion for engineering. Our slogan is Those Who Think, and we are based in Almaden Valley, San Jose, and you can see our logo on the top right of the slide. Finally, we are determined to logically think our way to victory in conquering this CubeSat challenge.
Next, I'd like to go over some of our SMART requirements. SMART stands for specific, measurable, achievable, relevant, and time-based. We made sure that all of these requirements do meet those criteria and have some sort of way of verification to ensure that we did in fact complete these requirements upon review. First, we have the requirement that the CubeSat shall be designed to capture and transmit Earth imagery at a resolution of at most 1 centimeter per pixel from our demo orbit on the gantry. And we can verify this through analysis, and we can demonstrate this ourselves through using the gantry with the CubeSat on it and by taking pictures of the ground below it. Our next requirement is that the CubeSat shall be designed to capture and transmit Earth imagery at a resolution of no more than 150 meters per pixel. This can be verified through analysis or calculation using data known about the camera's field of view, resolution, and the height of its orbit. We also would like to use the materials provided by us to be used by the BWSIX Lincoln Lab Institute, and this can be verified through a review of the parts used. We would also like to be able to capture clear images of the target area within each 20-second demo orbit on the gantry, one orbit meaning one run of the CubeSat from one end to the gantry to the other. The images must be of sufficient clarity to determine impacted areas, and this can be verified through a demonstration of a test orbit on the gantry. And we would also like to ensure that the CubeSat will fit the 1U 10 centimeter by 10 centimeter by 10 centimeter dimension requirements. And we can verify this by analyzing our design and ensuring that it will fit in those requirements, and also afterwards reviewing the built CubeSat to make sure it does fit that. We would also like to ensure that the CubeSat will be able to transmit data to the ground station in the form of images. And we can do this through our demo by transmitting the images and uploading them onto GitHub through our program, which we can then access through the ground station.
Alright, our CubeSat is going to be used in order to take photos of cities and check if areas are affected by power outages and report that back to the ground station. And this concept of operations is going to be describing the series of steps that we need to take to accomplish our mission and how it's going to combat failure along the way. It begins in the power off section where the CubeSat will be turned off, and once you turn it on, it is in pre-launch mode, and that's where it's going to begin its first series of self-tests. If the self-test fails, it's going to power back off once again, and if it succeeds, then it is going to go into launch mode and begin being sent out into space. Then, once it's deployed, it will be in orbit insertion and start a series of self-tests. If the self-test fails, it'll be an error contingency, and if it succeeds, it'll be an on-orbit on-station. And in error contingency, there's two options. If it fails, then the mission will be a failure. However, if that is resolved, it'll also go back to on-orbit on-station. Once in this state, if there's an error, then it'll go back to its series of self-tests. However, if it succeeds, then it'll signal the camera to turn on. Once the camera's on, if it can take a photo, then it'll start taking photos of cities, and if it can't, then that will also be a failure of the mission. When it's taking photos of cities, if it takes the photo, it'll have to figure out which areas have abnormal amounts of lights off, which we will be able to program to see what % of the light is off and what's its general range. And if it is not able to do that, it'll have to repeat that step and take more photos to make sure that the data is accurate and it can calculate that. Then, once it has figured out what those areas are and which areas have had power outages, it'll send that data back to the ground station so that it can be collected and analyzed.
Moving on, this is our CAD model. We began by modeling each part individually in Fusion 360 before importing all the parts into one document as shown here. For simplicity, we decided not to model screws and fasteners. We then assembled the CubeSat using Fusion 360's joint feature. Here, you can see our finished CAD model. After we were satisfied with the assembly of the CubeSat, we modeled the wires, allowing us to calculate the length of required wires, as well as visualize where each wire would need to go in order to keep the physical project neat with proper wire management. We also created these animations using some of Fusion's tools to allow for easier visibility of the internal components. This QR code leads to an online access to the CAD model in case you want to view it from other angles that were not shown in the slideshow. And here are the mass and cost budgets for the CubeSat assembly. Each item in the table directly corresponds to a component that will be on the CubeSat, as well as its associated cost and weight in grams. Each item in the table will have an amount listed, as well as a comment explaining what the item's use is. It is important to note that some hardware, such as the acrylic panels, are brought in a form that needs further processing, such as cutting or drilling, before being used on the CubeSat. Additionally, some items may come in bulk packages, which is reflected in the cost. However, the weight only represents the mass of the materials which will be used on the CubeSat, and not the total mass of all of the bulk hardware. As shown in the data table, the CubeSat can be expected to cost around $223 of raw materials and weigh about 462 grams.
So moving on to our power budget, this is our power requirements for our CubeSat in two different scenarios, both idle mode and startup mode. And as you can see in idle mode, the Raspberry Pi consumes 2.7 watts, while the battery consumes 10 watts, and both the camera and the IMU draw pretty minimal power, which gives us a total power usage of 12.72 watts in idle, while on startup, the power consumption of the Raspberry Pi rises to around 5.1 watts due to the increased processing demand, leading our total requirement on start to be 15.12 watts. However, our available power source is a singular solar panel, which can only supply 1 watt, which creates a significant power deficit. And as highlighted on the bottom, multiple solar panels would probably be required to meet the CubeSat's power demands. We also calculated the discharge times for the CubeSat, which was around 3.93 hours in idle and 3.31 hours on startup. And the battery capacity was 50 watt hours on the battery, and with a 1 watt solar panel, in optimal conditions, it would take 50 hours to charge the battery. However, with multiple solar panels, this may be a different value. Now let's discuss the link budget for our CubeSat communication system, considering a 400 kilometer orbit and a 1 megahertz bandwidth. So we'll be comparing two different scenarios, the uplink from the ground station to the satellite, and the downlink from the satellite back to the ground. And this is seen here separated by our uplink and downlink budgets on the left and the right. And what can be seen on our link budget, more specifically, are the positive and high signal to noise ratio values, which indicate acceptable and successful communication. And the high free space path loss value of 137.31 decibels is compensated by the antenna gains and the sufficient transmit power that can be seen on the budget. And there's also a very low noise power, illustrating stronger signal clarity. So overall, these budgets highlight the importance of optimizing antenna gains and power levels for successful communication, and neither the uplink nor downlinks dominate system performance.
Now for the data budget. The width of the image that is taken by the camera module is 4,608 pixels, and the height is 2,592 pixels. The bits per pixel for our image is 12 bits, and the data per pixel is 30 bits because of the use of RGB. We can find the pixels per image by finding the area using length times width, which is 11,943,936 square pixels. We can then find the size of each image by multiplying the data per pixel and the pixels per image, which equates to about 44.79 megabytes, which, when using a 10:1 ratio JPEG compression, we have an image size of 4.48 megabytes. Now, We know that the data rate is equal to the total data size divided by the transmission time. So if we want a time of 10 seconds per image, it requires 3.584 megabytes per second. If we want a time of 15 seconds per image, it will require 2.39 megabytes per second. And finally, if we want a time of 20 seconds per image, it will require 1.79 megabytes per second.
Next, I'd like to go over our system level block diagram. And first, let's talk about the power subsystem. The power subsystem consists of a solar panel, USB adapter, and a power bank. The solar panel draws power from the sun, which is then fed into a USB adapter, which then feeds into the power bank. The power bank then feeds to the Pi, and the Pi is the control system, which is a subset of the structure subsystem. The Raspberry Pi is connected to ground control through both SSH and Git. And the Raspberry Pi is also connected to the navigation subsystem, which consists of IMU BNO 055, which is our ACDS IMU. This gives us a gyroscope, accelerometer, and magnometer, all of which are very important for us to determine the positioning of the satellite. And the Raspberry Pi is also connected to the imaging subsystem, which consists of a Pi camera module 3, which allows us to take pictures. The structure subsystem consists of acrylic side panels, which are joined together by metal brackets. There's a solar panel mounted on the outside, and though we did list this in the power subsystem, we also listed this in the structure subsystem as it's an important component of the structure. Yeah. And the Raspberry Pi was listed as within the structure subsystem as it's an important structural component, although so is the power bank, which is connected to the Raspberry Pi.
So moving on to software architecture, in designing the CubeSat software, our focus is on detecting power outages effectively while avoiding any false alarms. So to achieve this, we need to account for many factors for our algorithm, which includes the time, whether it's day or night, as lighting conditions can naturally vary, the region or sections, are specific sections going dark, for example, so identifying specific sections can help us track down an outage. And light detection, so using LEDs in our simulation to monitor light levels, and identifying color changes, because detecting shifts in light color can indicate anomalies. So by integrating these elements, the CubeSat can accurately identify power outage events and communicate this information directly to the ground station, ensuring prompt and reliable monitoring.
Now for the integration and test plan of our CubeSat. First, we need to transmit light data from around the world in different cities and rural areas at night in order to calibrate the CubeSat on what normal lighting, and then it can define what the abnormal lighting range is for when we're looking for power outages. In the second step, it's important that the CubeSat takes different photos in different areas, and then it can match the lighting profile between the photos that it just took and what it was calibrated on in order to find what the difference is. And we can find the difference by setting a range of acceptable values because some nights will have more light, some nights will have less. And if the range of lighting in the photos that we just took in the CubeSat is a large abnormality, then we can flag that area as a power outage zone and collect that data to make sure that we have those areas as power outages. And then in the future, a modification that we can make that we don't have right now is wireless communication with the ground stations, which will allow easier transport of information between the two. And then we can also have flight adjustment, which will help redirect the path on areas that we want so that when it's in the orbit around the Earth, then we can get more relevant data on specific areas that we programmed rather than just taking the photos as it goes on its own path.